Let's do some calculations. Okay, here in the first circuit, we have 6,800 picofarads and 0.047 microfarads. It's a series circuit. So for figure A, the total capacitance is going to be 1 over 600 or 6,800 pico plus 1 over 0.047 microfarads, which is equal to, let's see, 6,800 EE negative 12, 1 over x plus 0.047 EE negative 6, 1 over x equals, so it's 1 over 218487395, which is equal to, press the 1 over x key, 1, 2, 3, 4, 5, 6, 7, 8, 9, about 5 nanofarads. The next one, this is a parallel. So for part B, total capacitance, I just add them up. So 10,000 microfarads plus 10,000 microfarads is 20,000 microfarads. C is parallel again, so I just add them up again. So it's going to be 330 picofarads plus 560 picofarads, which is 890 picofarads. Here's one here where the capacitors are going to charge to 18 volts. There's two capacitors. So the first thing we have to do is find total capacitance. It's a series circuit. So it's going to be 1 over 470 micro plus 1 over 33 microfarads. So it's 470 EE negative 6, 1 over x plus 33 EE negative 6, 1 over x equals, so it's 1 over 3243, 0.6. Press the 1 over x key. 1, 2, 3, 4, 5, 6, 30.8, 5 microfarads. So to figure out how the voltage divides, it's going to be total capacitance over the individual capacitor times the source. So it's 3085 micro divided by 470 micro times 10. So 3085 divided by 470 micro times 10 is 0.656 volts. And V2 is going to be 3085 micro over 33 micro times 10 volts, which is basically most of the voltage, 93% of it, 9.34 volts. Okay, so that would be V1 and V2. So once the capacitors charge, they will have that voltage on it. There'll be no current. Here's another one here. This is a charging capacitor because I have a voltage source. My time constant is R times C, so it's going to be 56 kilo ohms times 27 microfarads. So 56 EE3 times 27 EE negative 6 is 1.51 seconds. It doesn't seem right. Let me just try that again. 56 EE3 times 27 micro. Yep, that's right. So it's going to take, one time constant is 1.5 seconds. It takes 5 time constants for the capacitor to fully charge. So 1.51 times 5. So it's going to take about 7.55 seconds for this capacitor to charge. And the charging curve would look like this. You would have 1 time constant, 2, 3, 4, and 5 time constants. When you got here, you'd be at 12 volts. And let's say I want to know at one time constant, I'm going to be at 63% of my final voltage, so 0.63 times 12 volts, which is 7.56 volts. And I can do this for all of the two-time constants. I believe it was 84%. So it's 84 times 12, 0.84 times 12. You'd be at 10.08 volts. Here's another one. Here the time constant is going to be 680 ohms times 4.7 microfarads. So 680 times 4.7 micro, 3.2 milliseconds. So it's going to take a total of 5 times 3.2 milliseconds, which is 15 or 16 milliseconds, or 1592 milliseconds. And again, this is charging. It's going to reach 8 volts. It's going to take about 16 milliseconds to get there. Here, a capacitor. I can find the capacitive reactance here. This is the opposition to current. So I would just use this formula, 1 over 2 pi. The frequency is given as 50 kilohertz and 220 picofarads. So the reactance here is going to be 6.28 times 50K times 220 pico. 1 over x comes to about 14.5K. So this capacitor is exhibiting an effect of about 14.5 kiloohms. If I wanted to find the current here, I would use Ohm's law and just divide it by the reactance. So it would be 6 volts divided by 14.5K, which is going to be about 0.41 milliamps. And this current here is a RMS current, because the voltage I'm using is a RMS voltage. That's similar to the one we just did here. Total capacitance here is, I have these two are in series, so it will be 1 over 220 micro plus 1 over 330 micro, which is 132 micro. So I then have the 150 micro, and this is my equivalent 132 micro, and parallels I just add. So that's going to be 282 microfarads for that.